All right. So I think the sound should be working online. Okay, so thanks for the invitation. Thanks for the introduction. And yes, I'll be talking about neutron stars from an observer's point of view, because I do observation of neutron stars. And I'll try to explain how we use them as probes of nuclear physics. Yes. Yeah. Right. Okay. I'll start with a short introduction about neutron stars. I was told there are a lot of grad students here, and maybe you're not all very familiar with those objects. So they are extremely compact objects because of their small radii, very large masses, size of the mass of the sun, twice the mass of the sun. And if you combine the average radius of a neutron star with its mass, you end up with a very, very compact object. You may have heard the term pulsar, and a pulsar is a radio-emitting neutron star that rotates. And when the beam of radio emission passes in our line of sight, we see a blip in radio. That's historically how they were detected, how they were found. And the rotation of that neutron star, the periodicity of those radio blips made us think that they had to be small, very small objects. If you see something beeping every second or so, it cannot be an object the size of the Earth, like a white dwarf. It cannot be an object the size of a star. It has to be at least a few tens of kilometers at most. So this is how neutron stars were discovered. This radio emission comes from the open field lines of the magnetic field of the neutron stars, and this is where the emission comes from. I'll get back to this a little bit. This is just a way to show first pretty pictures, because those are the only pretty pictures as an astronomer that I would be able to show. And different wavelengths of observation where we see neutron stars, usually in the core collapse, in the remnant of a supernova explosion. There are not that many that we have associated with the supernova remnants, but in some of them you can see the little dot, the little point source where I put the laser at the center of the core collapse supernova remnant. In some cases, we see a pulsar at all wavelengths. This is the case for the crab pulsar. So we see radio pulsation, we see optical pulsation, we see X-ray pulsation, we see gamma ray pulsation all across the band. This is not really the case for all neutron stars, where the pulsation, we see the radio pulsar only in the radio band. Here we see a neutron star that does not have pulsation, but it's visible in the X-rays because it's hot. It has a surface temperature of 10 to the 6 Kelvin. So we see a hot, black body-like emission, but no pulsation, despite searching really carefully for radio pulsation, for X-ray pulsation in all wavelengths. We don't see any pulsation for that very young neutron star. What does that mean? Maybe the magnetic field has not fully emerged after the core collapse. This is a very young neutron star. We don't know. And this is one of the youngest nearby supernova remnants, 1987A, which you know. And there was a paper recently that there might be a neutron star at the center of the supernova remnant. Not a direct evidence, but there's evidence of photoionization of the material surrounding the center of the supernova remnant, which would mean some a lot of energy being emitted, which could come from the magnetic field of a neutron star, but we don't know this. And we use, yes, of course. Yes, so the question for people online, the question is whether the neutron star can move outside of its supernova remnant, and yes, this is very possible. Neutron star can be given a kick at birth during the supernova remnant, during the supernova explosion. If there is some asymmetry in the explosion, the neutron star can be given a kick. And we have some observation where the neutron star is actually off-centered or almost out of the supernova remnant. So we use them for extreme physics because they are extreme objects. They are very high compactness, so we can study gravity and test general relativity, for example, in the most intense regime. when they are in the binary system. Two neutron star black hole, neutron star white dwarf, all of those give environment where relativistic effects on the binary systems are really strong, and we can test relativity. They are really good particle accelerators. So when we see TeV cosmic rays, for example, this could be the site of particle acceleration, the supernova remnant. They have extremely high magnetic field, 10 to the 5, 10 to the 6 orders of magnitude larger than anything we can do on Earth. So that's a really cool environment for testing ENN. High temperature, I also mentioned this. And the topic of that talk is the extreme densities that we find inside neutron stars. So the nuclear physics that we can do with neutron stars. Oops, pass two. So this is a brief schematic version of the structure of neutron stars. We know about 1 kilometer. We can explain the physics of the first top kilometer of the neutron star with an ocean surrounding an outer crust and an inner crust. As you go deeper and deeper, then the nuclei structure is more and more neutron rich. Then you start to see superfluid neutrons beyond the neutron drift density. You have superfluid neutrons flowing around, let's say, in a crystalline structure of neutron-rich nuclei. And then inside the core, this is where all of the uncertainties are explode, let's say, where we need to try to quantify the interactions there, and the composition of the interior is also uncertain. We don't know if there is strangeness appearing inside, so with hyperons or kaons. We don't know if the matter can be fully deconfined, so we would have a soup of quarks and gluon inside the neutron star. The outside part is what we see, but we use the outside part and the macroscopic properties to probe the interior of a neutron star. And this has really huge implication for many fields. Nuclear physics, which I will go to this figure in a slightly bigger format right after. But this is also important for all the supernova explosion mechanism. The maximum compactness of a neutron star is important to understand how a supernova can actually explode, how the infalling material will fall onto the neutron star, bounce and bounce back and form the supernova. This is also important for the merger of compact objects, the events that will create the gravitational wave signals that we see during the merger of a compact object, as well as the produce of that merger. If those two neutron stars together will form a neutron star, a short-lived neutron star because it has a strong magnetic field that prevents the collapse, or directly a collapse to a black hole. All of those are questions that we can understand if we know that we can answer if we know neutron stars better. And all of the other topics as well can be understood better if we know what is the structure of a neutron star. For example, all the thermal evolution of a neutron star, how it cools down, how the magnetic field in the interior of a neutron star has an effect on the long-term evolution of neutron stars, and so on. This is the figure that I was showing just before that you may have seen, where neutron stars are somewhere around here, high density, large asymmetry, so 90% neutrons, 10% protons. And this is the rest of the diagram that most of you may know. This is a slide maybe that I show more to astrophysicists rather than physicists. So I can move on here and show you this one, which shows the equation of state for the pressure and the density. This is a selection of equation of states. The single lines are single model, and the bands are depending on the method of calculation. This band, for example, the blue band is chiral effective field theory. I think it's something that is 6 years, a bit more than, almost 10 years old now. But you can go from pressure density for a neutron star into a mass radius by solving the equation of stellar structure. So the hydrostatic equilibrium with the proper relativistic correction and mass equation or the continuity equation. You put that into this, and you solve those equations for a range of central density, and you obtain those mass radius curve that correspond to each of the equation of states that you want. So there's a one-to-one relation between a line here and a line here. So you can go either way you want. So if you want to constrain the equation of state, know what is inside neutron star, what type of material, what type of interactions, the strength of the interaction. What we need is to provide mass and radius measurements of neutron stars, ideally for the same neutron stars. If you have the mass for a neutron star and the radius for a neutron star, this helps, but ideally what we would like to have is this type of contours. Here you see a band here, which corresponds to the mass of a high mass neutron star, which seems to exclude some models. The ones that don't reach this band cannot produce a mass, such a massive neutron star, so that excludes the model. But ideally, what we would like are those red circles, which are not real measurements. You'll see that the real measurements we have are nowhere like this. How do we obtain this sort of band? We observe neutron star in a binary system in the radio band. So we use those radio pulsar that I'm showing. So this is here. And we have very rapid, here. Okay. Oops. We see the pulsation, and depending on the position of the neutron star in its orbit, the pulsation will arrive slightly earlier or slightly later. And you do this for a long extended period of time, and you can start probing, measuring the orbital parameters of that system. And if you measure the orbital parameter of the system, you can measure the mass of the two objects. Okay? This is true only when you have strong relativistic effects. Because if you don't have strong relativistic effect, you have a degeneracy between the masses of the two objects. But if you have strong relativistic effect, like the shrinking of the orbit, the precession of the orbit, or simply the gravitational redshift from the binary system, then you can break the degeneracy between the two masses and measure masses extremely precisely. And so this is the wrong reference. Apologies. Because I updated this to the most precise mass measurement of a neutron star. This is about 1 per 10,000. This is the most precise measurement of an astrophysical object outside of our solar system. And I'm not, so I think solar system measurements are better than this, but outside of the solar system, this is the most precise mass measurement. And we have, so this is a little thing that shows you that if you have questions about this, I have a lot of backup slides, but I cannot present too much detail about all of this. And this is a summary of all the masses, of most of the masses of neutron stars in binary that we know. They range from about 1.2 solar masses up to 2 point something solar masses. And you see that most of them are really good error bars, some of them not so good. That's measuring the masses, but as you can see on that diagram, measuring the masses is useful, but only if you have high masses. If you have a mass measurement that is at 1.5, it's consistent with most lines of equation of state. It doesn't bring you a lot of useful information. Why do I put animation? Let's take a white. So measuring the radius is actually much more useful for the equation of state, but it's also much more difficult. And there are many different methods. I started working on this for my PhD. There are a lot of different methods. All of them have systematics. All of them have lots of uncertainties. Sometimes we can quantify the uncertainties. Sometimes we just cannot quantify the uncertainties. We are in the dark. And so you see, those are all mass radius diagram, and you see different shapes that come from the different types of measurements and the types of uncertainties that are linked to this. If we want to measure the radius, so now I'll explain a bit how we measure the radius. You need to find a neutron star for which we can see the surface emission. You need to model that surface emission. And if you know the distance, then you can deduce the size of your object. This is thermal emission, so black body-like emission, by just looking at how much flux you have and knowing the distance. you can deduce the radius of that neutron star. The distances here are something like 1,000 parsecs, something like this, 1 kiloparsec, and the radius is 10 to 20 kilometers. So this is a bad ratio when you try to get light from an object, okay? A tiny object at large distances. So what you want to get enough flux is a high temperature. And high temperature means X-rays, 10 to the 5, 10 to the, more than 10 to the 5, 10 to the 6 Kelvin. And so neutron stars that shine at 10 to the 6 Kelvin, we see them in the X-rays, and this is your black body-like spectrum that we see. Those are the data points observed with the Chandra X-ray telescope, and the model on top of it of a neutron star thermal emission. In practice, what we see is not the actual radius of the neutron star, but the redshifted radius, redshifted by its own gravitational field. The neutron star is highly compact, strong gravitational field. So what we observe is not the neutron star radius, but neutron star plus this 1 plus z, this gravitational redshift effect. And this gravitational redshift depends on the mass and the radius, okay? Depends on the compactness of the neutron star, meaning that what we observe is something that is degenerate between the mass and the radius. This is a bit problematic. The constraint that we have from those type of X-ray spectrum, here in this formula that I showed before, it's not actual R, but it's this R infinity, which has the mass and radius degeneracy. And so the measurements look something like this. This is great, but if you try to put an equation of states, I mean, it can go anywhere. So unless you have really extreme R infinities that are around here or really large, all the canonical, the measurements that are around 12 kilometers, they do not allow you to really disentangle the equation of states constraint. And also, so you have this degeneracy. So here you have a problem of breaking that degeneracy. Knowing that the objects for which we see the surface, usually we don't have a mass measurement. There's no way to obtain a mass measurement from those. So we cannot break that degeneracy. But there are a few objects for which, and this is the topic of the talk, a few objects where we can measure the mass and the radius at the same time. And those are the millisecond pulsars that are here. Most of the millisecond pulsars are in binary system. And why is that? Because neutron stars, they are born around here. Sorry, let me explain the diagram first. This is a typical neutron star pulsar diagram, but this is in the x-axis is the spin period of the neutron star, millisecond, 1 second, 10 seconds. And on the y-axis is the period derivative, so the spin down of the neutron star. So slowing down very slowly, and at the top, slowing down very fast, okay? Neutron stars are born around here, and they evolve in that direction. When they cross that orange line here, which we call the death line of pulsars, they stop emitting. So since they evolve in that direction, in the diagonal from top left to bottom right, how do we have neutron stars here? Those ones are what we call the recycled neutron stars, and they are recycled by accretion of matter in a binary system. So by accreting matter from a companion star, the matter will transfer angular momentum and spin up the neutron star. So a neutron star will pass this death line, be recycled by the spin-up mechanism from accretion, and end up here. So here we have very old neutron stars that have been spun up by accretion and that are still in binary systems. The ones that are not in binary systems, so not in a square blue box, it's probably because they lost their companion from some mechanism. And those are interesting because here's what we see from those binary millisecond pulsar. We see the radio emission, the one that I showed at the beginning, which gives you the radio pulsar. And those are, this is what it is here. It looks this type of radio pulsar emission. We don't really know where it comes from, meaning at which altitude in the field lines of that pulsar. We don't really know where it comes from. Then we have gamma ray emission, which is probably curvature radiation, synchrotron radiation, far outside in the magnetic field of the neutron star. And those two, radio and gamma, if you want to try to probe the gravitational field of the neutron star, it's not very useful because it's far outside of the gravitational field. You want something that is close to the neutron star itself, the emission that is from the surface. And this is what we have with those hot region at the magnetic poles. This is hot thermal X-ray emission that we can see and gives us pulsations. Those hotspots at the magnetic pole, they are caused by return currents. So you have particles that are that travel in the magnetic field that are accelerated in the electric field induced by the magnetic field and bombard the surface right at the magnetic pole. By doing this, with relativistic speed, by bombarding the surface at those speeds, it will heat up locally the atmosphere of the neutron star. So we have an object that is fairly cool all over, but at the hotspot, at the magnetic poles of the neutron star, we have 10 to the 6 Kelvin of temperatures. And so what happens when you have very localized hot emission on the neutron star that rotates? You're going to see the hotspot, lots of X-rays. You don't see the hotspot. You see the hotspot again, okay? So you have variation of the X-ray flux as with the rotation of the neutron star. This is what is shown here. You see the spot, brightness increases until it drops below zero. Except there's one effect that is not taken into account here, general relativity. The main effect is that the photons emitted by the hotspots are going to have a trajectory bent by the neutron star gravitational field itself. Meaning that when the hotspot is here, you see it. When it's here, you still see it because some of the photons will go toward you. When it's here, if the compactness is high enough, some of the photons will still go toward you. And you can see a hotspot even at the back of the neutron star. And this is what it looks like here. Those are two neutron stars with the same mass and radius, so the same compactness, except here gravity was turned off, so no light bending of the photons. And here the gravity was kept, the trajectory of the photon was calculated properly, meaning that at the back of the neutron star, you see the spot. And what it does, it changes the shape of that X-ray light curve as a function of rotation. So if you can model this, you can get back to the compactness of the neutron star. Okay? You will measure mass and radius because the shape of the light curve depends on this ratio mass over radius. And then there's another effect because we want to try to break that degeneracy between mass and radius. The other effect is simply the Doppler effect. If you have a spot that is coming out of the eclipse toward you, it's going to be blue shifted. The spot that is going away from you is going to be red shifted. We are talking about neutron stars that have millisecond rotation speed. So between 200 and 500 hertz of rotation. The effect, the Doppler effect, is strong enough that it can be measured. And so with that, we can break the degeneracy between mass and radius because that effect only depends on the radius. It does not depend on the mass. It only depends on the distance from the rotational axis and the angular velocity of the neutron star. So we have all the ingredients to do this. Now we need a data set, and we have data from the NICER, the Neutron Star Interior Composition Explorer. It's an X-ray telescope. They need to be above the atmosphere, otherwise no X-rays. And it's on the space station, and it looks like this. It has 56 concentrators to concentrate X-rays, because X-rays pass through mirrors, obviously. So you need some clever optics to be able to bounce them at grazing incidence onto your detector. This is what the data set for those pulsar light curve that I was showing, the schematic that I was showing here, looked like with the previous type of instrument. And with NICER, we have an instrument that is dedicated to this and much more sensitive. So the quality of the data increased a lot. And in addition to this, we have we can measure photons as a function of rotation, but we can also measure the energy of the photons, meaning that here we have the spectrum. So for each phase bin, we have a spectrum of the neutron star. And this is important to measure this, because without the spectrum, we cannot break the degeneracy between mass and radius. Okay? So those are the ingredients, and I cannot go into the detail for all of them. We have the data set that I just talked about. This is just to represent the fact that we have a ray tracing modeling for the trajectory of the pulsar of the photons from the neutron star to the observer, which depends on the compactness. We need to have a model of emission for the surface emission. So both the fact that it's black body-like emission, it's not quite a black body, there's an atmosphere, so we have an atmosphere model. And the size, the spot, the shape, and the temperature of the spots have to be modeled as well. So we also have a model. It's not just not necessarily two spherical spots that are antipodal. So we need to have a model for this. And this is some instrumental aspect that I won't go into the detail. And then in some cases, we also have priors on the distance, prior information on the mass or the inclination of the system, which really help. 5 minutes. Okay. So I'll show some results now. The first two pulsars that were analyzed and published, this one, we found a radius that had 12.7 plus or minus 10% uncertainty, something like this, and two spots that were not perfectly circular and perfectly antipodal, but one small circular spot that was giving us the secondary peak, and the main brightest peak came from a very elongated crescent-shaped spot. Why? We don't really know. What we know is that the magnetic field of those millisecond pulsar is not very dipolar. It's probably like an offset dipole. There are probably some quadrupole components, which could give this type of shape here. Some people that are working on magnetic field structure of a neutron star can sort of reproduce this type of shape by putting an offset dipole with some quadrupole components. Yes?
Spot is this, or is this an inverse problem? You did a bunch of modeling and found that.
Yes. So the question is, how do we arrive to that spot shape? What we started with simple circular spot. The data was not fitting well, so we started complexifying the model by putting an annulus with a central part that is hotter and a ring that is colder, or vice versa. And then the ring was made by having two circles that overlap, but one of them at a temperature so low that it basically did not contribute, and most of the contribution was from the outer sliver of the two overlapping radius, and that's how we. And so we complexified the model progressively until adding complexity was not improving anything in the data set. So that's the only way we can really do it for complexity of the calculation. Yeah, we can talk a bit more about this. Okay. Then the second pulsar, this one was really interesting because it was much fainter, but we had a very good prior on the mass. It's a very high mass neutron star, so very high. Yeah, it's a 2.1 solar mass neutron star. And we found a radius of around the same type of uncertainty, despite being a much fainter, factor of 10 times fainter neutron star. And this one, the data set was not as good, but so we could not really tell extra complexity on the hotspot. So it was compatible with two simple circular spots. So if I put those constraints, those two radius constraints on the mass radius diagram, this is where they are. This is the first one, and this is the second one. For each of those two, there were two different independent teams that did the analysis, and both are compatible. This is just a different choice of prior upper limit, but it's not that important. One thing you can notice is the difference of the shape. Here, this is an horizontal ellipse. This one is inclined. Because for this one, the bottom one, we don't know the mass. So we did not have any prior information of the mass. Here we knew the mass was at 2.1, so we used that prior information. Here we didn't, so we had to infer the mass and break the degeneracy with that Doppler, with the fitting of the Doppler effect that I talked about. So this is the first time that we were able to measure the mass from a neutron star that is isolated. It's an isolated system. We don't know we don't know any binary information, so we don't have a prior on the mass. So for the first time, we measure the mass of a neutron star in an isolated system. Okay, and this was also compatible with other analysis that I did with some colleagues, including Jérôme, this one by a former PhD student of Jérôme. Different methods, but I don't have too much time to go into the details. Those two pulsars were reanalyzed with more data. Things did not change too much, adding 1 megasecond of observation, so that several weeks of observation shrunk a little bit the contours. Because here we're dominated by background. So even if you double your exposure time, you're not going to gain too much. This one, the improvement was a bit better when we used additional data from another telescope. This is also some long discussion about background and constraints that won't go into the detail. Then there was this neutron star. This one was basically the poster child of NICER. It was supposed to be the first neutron star to analyze, and it turned out to be a much more complicated. But after 6 years of data collection and analysis, we finally published it with a radius with a 7% uncertainty. So this is the best so far, and this is where it is in mass radius space. I'll show it compared to the other, and you see that we also have a very complex geometry. A small spot with a very hot core and a ring at the pole. This is weird, but this is what the model gives us. And if I put it on this mass radius diagram compared to the other one, it's around here. We know the mass, so that's why the ellipse is horizontal compared to the other. Then there's this one, which I will not show because we are recommending nuclear physicist modelers to not use the result for this one. It was extremely complex. The radius were all over the place depending on the model and the background assumption that we used. Please, if you use neutron star mass and radius measurement, do not use this one. Okay, and I won't show it for that reason. Yes.
What do you mean by this one?
So this one here, the blue one that I'm not showing here on purpose.
Oh, okay.
Okay. All right. So then, when you have those mass and radius measurements, you can infer some constraint on the equation of state. There are many different ways to do it, many different approaches. Probably people here, including Jérôme and others, know more about how this is done than me. But by using, for example, a parametrization of the equation of state and doing the inversion, you can go sample your mass radius space compatible with those 3 measurements or the gravitational wave measurements and infer the equation of state in density, in pressure density, or in mass and radius. This shows here just basically the nuclear physics prior in blue for this particular model of Carroll field effective theory, and adding the data from those 3 neutron stars gives you the green band that is in the center here. There are many other works. I started listing them all, and then there was too many, so I chose to not show any references. Many people are working on this, exploiting the NICER data. We have more measurements coming, and I have 8 minutes left. I have a postdoc working on this particular neutron star. You can see the data set is not really amazing. There's a lot of noise, but the pulsar is here for sure. But it's an isolated pulsar. So again, we'll have to measure the mass and the radius based on the Doppler, the Doppler way to break the degeneracy. I don't know if the results are going to be extremely constrained. Then there's this one here that my PhD student Lucien Mauviard is working on. This one is interesting because it has a mass measurement. And so this is the height of the ellipse, the blue ellipse, is about the uncertainty on the mass measurement. And the width here gives you the uncertainty on the radius. The paper should be submitted in a few weeks, but I've been saying that for a few months. So very soon you'll see the radius. It's around here, centered, aligned with that other pulsar of 437. Slightly larger uncertainty because it's a fainter pulsar. And then this one is going to work on this one here. There is a pulsar. Believe me, there is something. There is a little bit of extra emission here. It's faint, but it's a very massive neutron star with a really, really precise mass, much more precise than this one. So we're hoping that even if the signal-to-noise of the pulsar itself is low, the high constraint on the mass will be useful. So stay tuned for those. This is about the limitation of NICER, something like 5 sources. We have a few more even fainter pulsar that we can try to analyze. But this is just a handful of pulsars, 6, maybe 8, to produce mass and radius from. So the question is, in the future, what are the facilities that will help us measure mass and radius, measurement of pulsar to infer the equation of state and constrain nuclear physics? There are 2 missions. This one is a Chinese mission for the 2030s, roughly, with a little bit more sensitive than NICER. It's actually not 4 or 5 now, it's 2 or 3. And I need to update that slide. And the next one is New Athena, the European next generation X-ray telescope. And this one is really going to change the game. Why? Because it's about 5 times the sensitivity of NICER and a much lower background. So this is the background. I will show you for comparison some simulation that I did with this upcoming telescope. I should say that you'll need to be patient. The launch date is for 2037. So we'll have to wait a bit more, but this is going to be a game changer. This is the simulated data for that pulsar with Athena. This is, in comparison, what we see with NICER. We have in the spectrum here, so just showing the distribution as of the events of the photons that we see as a function of energy. We have about a 1% background with Athena. With NICER, it's the opposite. We have 99% background and 1% or a few percent pulsar photons. So we are really, with NICER, we are trying to fit pulsation on top of a huge background. Here, this is the opposite. We have a very low background. Yeah. That's an excellent question. What is the background? Maybe, yeah. So the background it's a mix of everything. There's particle background because we have a telescope that is flying in space. So the detectors are hit by particle. We have the diffuse cosmic X-ray background. All the sources that are unresolved, that are shining in the X-rays give a diffuse noise. Instrumental background because we have detectors that are quite sensitive. And then you have, depending on the instrument, you have other sources in the field of view. For example, NICER. Well, I'm not going to change. NICER is a non-imaging instrument. So it sees all photons from all sources within 6 arc minutes in the sky. And so we see photons from other sources that are giving contamination. In comparison, Athena will have a point spread function. So the field of view, the angular resolution will be 5 arc seconds. So there you will see only your source, no contamination from the nearby sources. And that will change also a lot. Does that answer your question?
Much smaller.
Yes. Yes. It can separate on a much smaller scale. Yes. So we did some simulation with Athena using the result from that pulsar that we measured. And here, lots of maybe I should change that slide maybe, but the key information is that with Athena, in 500 kiloseconds of observation, which is a long time, we can get about 3% uncertainties on the radius, compared to 1.6 megasecond of observation with NICER, which give us 10% uncertainties, plus or minus 10% uncertainties on the radius. So this will change. This will really change a lot. And again, this is a faint pulsar. So for the brighter pulsar in that exposure time, we should reduce even more the uncertainties. So with that telescope, we can get few percent uncertainties on 10, 15 millisecond pulsar for equation of state constraint. And then I will finish with 2 slides with another method that a PhD student of mine is working on. Not looking at the hotspot, but looking at the rest of the emission. The rest of the emission is much colder, like I was saying. The hotspots are heated up by particle bombardment at the magnetic pole. The rest of the surface is much colder, 10 to the 5. And at 10 to the 5 Kelvin, you shift your emission, not from the X-rays, to in between the far UV and the X-rays. And so we did some analysis where we use the far UV observation, which is the Rayleigh-Jeans tail of the black body, and a bit of the X-rays here to fit the spectrum of the rest of the emission of the neutron star. And from this, we can constrain the radius, the size of the neutron star. It only works for the closest ones. If they are too far, this emission or especially in the UV, is too low, so we don't see anything. But this works really well, and we have a paper that is about to be finished for that pulsar PSR J0437. So the green contours are the NICER results, the ones that use the hotspot and the pulse profile, and the purple results uses the far UV data and some X-ray data as well. No NICER data involved, and we are smack on the same radius. We are slightly broader in mass because we use a different mass prior, but if we were to use the same mass prior, it would be the same thickness of contour. So those results will be published by Pierre Stamler in a few weeks. No, maybe a bit more for this one. All right, I'm arriving at 40 minutes exactly, and so this is my conclusion. So this pulse profile modeling technique that was made by NICER, that was made possible by NICER, was really a proof of demonstration that next generation telescope will be able to apply to a large sample of millisecond pulsars. We have other techniques like the one I just showed to try to complement that as well, trying to get mass and radius from different types of sources as well to confirm what we measure with NICER. Yeah, that's it. What we hope is to go from this to something that will look like this in the future, few percent uncertainties, and maybe to see a phase transition. I don't know. They say this is a false figure, obviously, but maybe we can reach that in 10 years, 15 years, something like this. Thank you.
Fascinating thought. Are there any questions?
Thank you for the talk. Very interesting. I'm curious about the diffuseness of the radius, like there's an atmosphere. How much does that affect the uncertainty in the radius?
Plus or minus 1 centimeter. The atmosphere is about this thick at the top of the neutron star. I think we are quite far away from it. Yeah. So the last scattering of the heat from the inside going through the atmosphere happens in the last centimeter. It's so dense that yeah, very small. There's probably more uncertainties with the crust itself of the neutron star than the atmosphere.
Yes, please.
Yeah, I'd like to, can you show the previous slide where you show an alternative method?
Yeah.
So since this method, you don't need the NICER data, in principle, you have other pulsar that fit into the criteria that you may use, right? So you can have more, you can do the air bar maybe if it's larger.
Yeah. So the question is, with that second method where we don't need NICER data, we should have more pulsar where this is possible. Yes, but we will be limited by this. Basically, there are something like a total of 3 pulsar for which we see far UV emission. Because this is cold, this is a small source, and the only UV telescope that we have to observe this is Hubble, which is not that big of a telescope and will be decommissioned in not long. So this is the best data set we have. There's a handful of pulsar where we probably have 2 data points. It's better than nothing, no? But we will not be able to apply it to many pulsars, for sure. Oh, I need to repeat the question.
Can I let one of the students ask? Did you start to want to?
Has the James Webb Telescope affected any or influenced at all for stellar evolution or neutron star evolution?
So the question is whether James Webb has affected any of the research on neutron star. Yeah. It's hard to answer that question because neutron stars do not emit a lot in the infrared. James Webb is an infrared telescope, so if you follow that line and you extend to infrared emission, there's no way James Webb can see anything. But it can help us constrain the binary companion of a neutron star. So if you have a neutron star in the binary system, for something, let's say you could not, from the neutron star itself, you could not constrain the binary parameters precisely enough, then with James Webb, you could constrain them with the binary companion. So the binary companion, if it's a normal star, a main sequence star or something like this, it can be seen in infrared, And there you could do techniques like spectroscopy to constrain the binary parameters. So there is some indirect neutron star physics that can be done with James Webb, but not direct observation of the neutron stars.
Did you want to ask? So you.
Yeah, so I have some question about your hotspot. So your first explanation of the hotspot, that you mainly see the hotspot from the pole because it was hitting up the pole,
Yes.
right? That's a very simple, and I understand it. Okay. But then the problem is that if that's really the only hotspot, it will depend on your site or like your inclination where your
Yes.
site is.
Yeah.
So that's one. The other thing that
So to answer first, the first question is this hotspot will depend on the inclination. Yes, we do fit for the inclination. This is one of the three parameters if we don't know it. For some pulsars, we do know the inclination because we see the radio emission and we can constrain the inclination. Okay. So next, yeah, you can go for your next question.
Well, what's your model for two hotspot or strings shape hotspot? What's the model?
So the question is, what is the model for weird shaped hotspot? Let's say. I don't know exactly because I don't do this type of modeling, but if people that do this, if instead of putting a dipole that passes right through the center, if they offset it from the center of the neutron star, then the areas where the magnetic field hit the surface will be elongated, and that's how they can reproduce those crescent shape. That's what they show. I don't do this myself, but it seems to be explained in some ways. And if you offset your dipole, you need some extra quadrupolar component. Yeah. Let me see if I have a figure. Ah, that's mine. No, I do not have extra figures. Sorry. Okay.
That was the explanation for multiple hotspots.
That's the explanation for different shapes, for non-circular shapes. Yes.
I see.
Yeah.
Okay, when the different shape maybe.
In those analyses, we mostly model two hotspots only, and this is because we see two pulsations. There could be a third hotspot that we don't see, and that doesn't cause pulsation, but we start with two.
Okay. Patrick.
So I'm really curious about this inverse problem. I guess it's related to the type of question. So you have all these models that you feed together, and then are these? You said these are quite expensive, right?
Yeah.
Do you use any sort of emulation for this at all?
No, we just go brute force sampling. We're starting to look into different approaches like SBI and things like this, but until now it was brute force multi-nest, if you know that the nested sampling, and we just for each set of parameters do the ray tracing, the calculation of the atmosphere, ray tracing, and infer the mass and radius and all the other parameters, size of the spot, location of the spot, temperature, and so on.
So I assume you probably bootstrap your uncertainties through this inverse problem, or maybe something more sophisticated.
No, it's not also sophisticated.
Okay, so then how do you, or do you have a good estimate on how much of your uncertainty is from the fitting of the inverse problem and from the data? Because you seem to make a big point that the data is very noisy and we really like a better telescope out there, but is that actually the main source of uncertainty?
It's not an easy answer, and you can imagine that. Maybe I have a slide for this one as well. One example, I should not. Maybe I don't have it. No, I don't have it. Yes, I do have it. Perfect, but it's a hidden slide. That will partially answer your question. Those are the two results from a neutron star, 0030, the first one that we studied with more data. And then we found two solutions that are equally good and that give radius around between 10 and 13 or between 12 and much higher. Two different geometries, equally good results. And we don't know what to do with this. What we concluded from this is that it's great to have the mass. Having a mass prior helps. This is the neutron star for which we don't have a mass prior, and this is a mess. Because of that, it's a mess. When we have the mass prior, all the results are much more stable. So yes, the choice of hotspot models is a pain. And ideally, we would go free of this and be completely agnostic and see what any spot shape could be, but this would be much more expensive in terms of calculation. I hope I answered your question because it was a multiple topic questions. And in terms of background, there are ways to constrain. Did you ask about background? Yes. No. Okay. No. You talked about noise, but yeah. Okay.
Okay, Andy.
Okay, so with the geometries of the neutron stars, those are the hotspots are like where the poles are, right?
Yeah.
Okay, naively, I would think there'd be like where it'd be like the Earth, where it's like they're perpendicular or not perpendicular. It's like a line through. Why aren't they a line through, or is that like that emergent from something, or is that?
You mean why from the rotation axis?
Yeah, from the rotation axis.
No, if the magnetic field was always aligned with the rotation axis, we would never see pulsations because it would always shine in the same direction. The fact that we see pulsars in the radio, in the X-rays, is because the magnetic field is at an angle from the rotation axis, so you have this lighthouse effect.
Right, but they're
So maybe I misunderstood your question then. Sorry. As you wish, yeah. Okay. Sorry.
Two more questions. Julie?
Mine's very long. Could you have a meteoroid-like thing speed on the neutron star?
Could I have what?
Meteoroid-like thing speed on the neutron star. Probably mine.
I think this is one of the theory to explain fast radio bursts. I've seen that some planetary debris hitting the neutron star that would cause a fast radio burst, like those really short blips of millisecond long, extremely powerful emission of radio. I don't know if this is realistic or not, to be honest.
Any other questions? Maybe like one more question.
This is a bit of a maybe unfair question, but would it be possible, or have you considered this hotspot modeling to be time evolving as well?
It's an excellent question. Is the hotspot evolving? The answer is with the datas. Well, making data plural. With the data sets we have, there's no indication of this happening. Why is that? Because the pulses are extremely regular on really long time scales. First, the radio pulses have been the same for some pulsars 20 years. It hasn't changed. So that means the magnetic field does not swing around too much. I mean, it swings around with the neutron star, but there's no deformation of the magnetic field. Then the X-ray pulsation, which come from the surface, so which come from the hotspot, we don't see any change of pulsations, change in the shape of the pulses. So let me see if I can. Yeah, it's really hard on an angle. Data here. This is data from 2018, 2020. This is data from 2008. So there's 12 years of difference. The shape within the statistics, obviously, the shapes are exactly the same. If the spots were migrating, evolving in shape, one peak would become brighter, would shift in phase. So there's no indication of that, but it's a fair question. So far, we cannot tell anything. We cannot see any evolution.
Okay. Let's thank Sebastien again.
Thank you very much.